Okay, so things that we should have gone through already, we've ticked off here already, but let's talk a little bit about this half-life stuff. Um, so we're looking at these sections here, and the half-life, let's give you a definition. Two slight variations of the definition. I'm taking for the activity, and that's like the number of little particles that are coming out per second. And the other, the second slight variation on the definition, instead of activity, we could have number of unstable nuclei. So pretty much the same definition, but you can just talk about either of those two different things. So if we think back to that tremendous example that we had of our glass soap bubbles, and let's say that we've got, I don't know, about 1,000 soap bubbles in this beaker or in this glass. And let's say, for example, the on average, well, let's not worry about averages and times and things. Um, these bubbles are only going to last for a certain amount of time before they burst. But right at the very, very beginning, we should probably get the most number of bursts. Because we got so many bubbles that are there, really likely we're going to have a lot more bubble bursts than we would if we had a smaller number of bubbles. So if we were to look at the number of bursts, at the very, very beginning, we should be getting a large number of bursts per second because we've got a large number of bubbles. But as we run out of bubbles, well, then we're going to have less bubbles to burst, so we're going to have less bubbles bursting per second. And eventually, when we've only got like sort of one or two bubbles that are left, we're going to have pretty much no bubbles bursting per second. And we get a sort of graph that would look a little bit like that. Let's get rid of those points over there. So we should be getting what is called an exponential decay. Now, for the maths wizards among you, I can show you what the fancy IB level equation is. If you don't like fancy IB equations, you can close your eyes now. But we would talk about this as being the activity that we measure in becquerels. And we could say that the activity is going to be equal to the starting activity with some exponential e to the minus, what is it, lambda t. So we've got like this section here is sort of like the half-life. It's not perfectly the half-life. You need to do some logarithms and stuff to get the half-life. But when we talk about the half-life, that should be the amount of time that it takes to go from like 100% of the starting number to half of that value. We can say that this time is a half-life. Now to go from 50% to 25%, if I've drawn this properly, it's not brilliant, it's not terrible. This amount of time here should be another half-life. And if you go from a quarter down to an eighth, well then this amount of time should also be a half-life. So we've got this really, really nice predictable pattern where we could go forward in time, or we could be able to predict how much there would be after another half-life. So let me draw another nice big example, should be using straight lines, too lazy. So let's say that we had 360 things, 360 unstable nuclei. Probably would be 360 billion. Normally you're talking about much, much bigger numbers. And let's say that we had half-life. And half-lives can be really short or really long. It depends on how unstable your sample is. So let's say we had a half-life of, I don't know, let's put it in seconds because it's easy. So we start off with 360 things at the very beginning. And if we've got the half-life, it's the amount of time that it takes for the number or the activity to decrease by half. Stop that. So after 1 second, how many of those things would we have left? Oh, you're walking quiet. After 1 second, if you start off with 360, you'd expect, oh, well done, one of you is awake. So that'll be after 1 half-life. After another half-life, how many would we have? Seeing a pattern yet? The same. So we would have 360 down to about 180 down to about there, to there, to about there. So we're going to get exactly the same sort of shape. And really, we're going to get the same shape if we change like the amount of time, or we change like the overall starting number. We might get a slightly taller or slightly wider graph, but if we change the scale, we're going to get exactly the same shape. So a standard question that, or two standard sort of question types that you might be asked would be, let's say you've got a, oh wait, sorry, one thing I should have mentioned. If you're talking about numbers of atoms, you shouldn't be able to have half, or sorry, not atom, nucleus. You shouldn't be able to have like half a nucleus. If you're talking about the activity, well, that's okay. If you're talking like on average, like 14.5 counts per second. So let's say a sample of uranium as an activity of 1400 becquerels. Half-life of 3 days. You could be asked really two different sorts of questions. Oh, sorry, not how much. What will the activity be? And let's say 9 days. And we could also ask, what was the activity, let's say 12 days ago? Because we don't just use this going forwards in time to have a decrease. Because we know what the pattern is, we can also look at it going backwards in time and be able to figure out what the activity would have been with some other number of half-lives in the past. So I don't know if you're working along. I'm recording this, so I'll speed it up. So we know that the half-life is 3 days. So in our 9 days, we're going to have 3 half-lives. Because we're going forwards in time, we're going to be decreasing. So we have a starting activity of 1400. And then we'd have 700, then we'd have 350, then we'd have 150, 160, 75. So that'll be 1 half-life, 2 half-lives, 3 half-lives, will give us an activity of 175 becquerels. Now, if we're going backwards, well, then we need to do it the other way around. So this time we've got 12 days. The half-life is still 3 days. So that's going to be 4 half-lives. We're going backwards this time. So we've got 1400. Somebody help me out. Thanks. 1, 2, 3, and then we got 2, 2, 400. So that'd be 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. So we would expect that this sample would have an activity of 22,400 becquerels if we had looked at it 12 days ago. Now this stuff's pretty useful because you can use it for something called carbon dating. There's one particular isotope, radioactive carbon-14. You all contain it, you all contain a little bit of it, and you all contain pretty much the same percentage of it. So I'll have a lot more because I'm a lot bigger than you are, but we all have the same percentage, and it constantly gets like swapped in and replaced when you're breathing and respiring and eating food and stuff. All trees and plants and animals and things, they all contain it as well, but slightly different percentages. And if we dig something up that's very, very, very old, we can have a look at the percentage of carbon-14 that's in it. This thing has a half-life of about 5,700 years. So we can look at, let's say we dug up an old piece of leather or something from some Egyptian site, and we know that for like the 5 grams of the leather that we have, we should have a curve like this. If we find out we've only got the activity that's here, then we can track back and we can figure out how long ago that sort of cow was killed to be able to make that piece of leather. So radioactive carbon dating is a very, very useful thing. Does anybody have any questions about that? You don't have to shout them out. You can type them in the comments. No questions at all. Oh no, how disappointing. Okay.